next speaker is Michiel Tukker. Michiel Tukker is a researcher at Deltares. It's a Dutch institute, research institute for water management. Michiel is also in charge of the development of Wanda. It's a Untitled software package. And he's going to tell something about large-scale experiments.
Thank you for the introduction and for the invitation to be here. Like I said, I am Michiel Tukker, and I'm going to give you an overview of a research project that started 2 years ago, and is actually still ongoing, for validating a 1D numerical model for compressible flows. First of all, let's give you some idea of what Deltares is. Some of you may know Deltares, some of you may not. We are a Dutch research institute, founded in 2008, and actually a fusion between 4 other research institutes that existed long before then. And we focus on 5 themes, essentially flood risk, sustainable planning, so policy issues, infrastructure, water and subsoil resources, so basically dikes, and environmental issues. Now, I'm working in a department that is actually operating in the infrastructure theme. We are called Industrial Hydrodynamics, and we focus on, as you see here, the industry, the power and desalination markets, sewage, urban drainage systems, and in those markets we mainly look at the pumping stations and optimization of approach flow for pumps. Detailed hydrodynamic modeling of weirs, of outfall systems, and also the intake systems at the start of the intakes. We're also active in the water transmission industry and in the sewage industry, where we mainly operate in water hammer studies, surge protection, and optimization of pipeline systems and pumping systems. We also have a lot of experience there in air entrainment, in sediment issues, some multiphase flows issues, of course. A few years ago, we have concluded a large-scale research project in the wastewater industry called Kaplat, that was focusing on air pockets in sewage systems, which actually reduced the capacity of the sewage systems. And it was a major issue within the Dutch water boards. Recently, we've also been active in smart thermal grids, so district heating systems, district cooling systems, and operating them in the most efficient way. We've also been very active in software development. We've developed the Wanda 1D numerical code for water hammer studies, flustering, which is actually fluid structure interaction code, and recently we've also been active in online monitoring systems, operator training systems, the more advanced uses of a hydrodynamic model. Now, due to our relations with other engineering companies, since 2005 we've been working on simulating and modeling gas transients for the NAM, the Dutch Hydrodynamics. This is an overview of the project that we've done across the Netherlands. Most of them, of course, in Groningen, where most of the gas production is. And this is an example of a typical project that we do. Usually we work on the gas production sites, not so much in the compression blending station, but it has most of the same properties. In our model we would have a reservoir, or a gas reservoir, a high pressure system up to a choke valve, and then a low pressure pipeline for transport to the plant. Now, these high and low pipeline systems are usually disconnected by the choke valve, but during incidents you can actually have a situation where these two are suddenly connected to each other, usually by a choke valve breakout. Of course, the pressure rating of the equipment is used as needed, so for the low pressure system you don't have the high pressure ratings, and this is of course an issue because you actually have the risk of damage to the pipelines. Now, normally when we start of these projects, they usually asked for pressure relief valves to be installed, and we do the sizing for that. And in the later studies, we actually looked at the safety protection systems, the safety instrumented systems, or the HIPS valves, which is basically a shut-off valve that switches, that closes on a certain pressure. We would then do, of course, we would determine the trigger level for that HIPS valve. But an additional issue that we had in these projects is if you have a liquid slug somewhere in a transport pipeline. Now, due to the liquid slug, you can actually get a reflection of the pressure wave, and that would cause an even higher incidental pressure in the pipeline. Now, to do these studies, we developed an additional module for our Wanda software, called Wanda Gas. This is, in the meantime, it has developed into a full-fledged module. We plan to release it somewhere next year. But at the moment, it is still somewhat in beta stage. And it is a 1D code for calculating fast transients in the complex branch systems that you can have. Or it also works for a single pipeline, of course. We use the method characteristics to compute the pressures, and we include full thermodynamics, so also the heat with the surroundings and heat exchange in the gas itself. And it uses an ideal gas law with some of that compressibility to come to a real gas law. Now, one of the strong points of Wanda is that we are constantly trying to validate our code. We're constantly performing laboratory experiments or looking for field experiments that we're allowed to do in order to check whether our software actually produces the correct results. On the left, we have a picture from a large-scale laboratory experiment that was done in the 70s, the predecessor of Wanda actually, where we were looking at cavitation due to pump trips. And you can actually see the blue line is the simulation and the red line is the measurement. You can actually see that there's a really nice match between those two. So we're really happy with that. And here on the right, you actually have a validation experiment that was based on SCADA measurements on a live oil platform, where they had an incident, and we could use the SCADA data to validate our software. Now, Wanda Gas is actually a completely new module, so it's not validated yet. We don't have validation code. So we decided to start out an experiment. Like I said, we usually use this software to simulate the choke valve breakout in a gas system. So you suddenly have a high pressure system connected to a low pressure system. We also wanted to see the reflection of the liquid slug. So we added a local depression in the system filled with water. We added a fast valve, which opens in a few 100 milliseconds to simulate the breaking of the choke valve. And of course, you need a long pipeline system to do all this. You cannot just use anything. And we were in luck because in early 2013, after a few years of construction and arguing with the contractor, we commissioned our pipeline system for multiphase flow research called the Alpha Loop. It is a 285 meter pipeline. We are working with the DN200 diameter, so 200 millimeters, rated at 16 bars, maximum pressure. For this experiment, we also selected a 60 cubic meters of air vessel. That was already existed at our site, but it was connected to the system for these experiments. And we also have a 25 cubic meters separation vessel to separate the water and air for these experiments. And for this project, we actually tested 3 variations of the system. I'll discuss all 3 of them in one go, but we tested 3 variations of the pipe. Now, course, we need some instrumentation to do this. So we installed pressure and temperature sensors in the air vessel, in the base of the system, where in the high pressure system, as it were. We had pressure and temperature upstream of the liquid slug. And we had pressure sensors downstream of the liquid slug to record the slug coming through, and of course the pressures during the system, during the experiment. For these experiments, we developed new void fraction sensors. It's basically a water level sensor. You see it here on the right. It is a metal ring with two metal wires in the center, and using that you can measure water level at very high sample rates. This is actually, essentially it is the economy version of a wire mesh, which is frequently used in the university for void fraction measurements. But only here you only have a vertical water level and not a full 3D or 2D image of the void fraction. The advantage is, of course, that these things are a lot cheaper than a full wire mesh. We also, of course, recorded pressure at the receiving tank, and we tried to record mass flow rates, but that didn't work due to a variety of reasons, which I'll get into later. And let me tell you what is the actual experiment now. In the beginning, the main air vessel is pressurized at 1, 2, or 3 bar G, and the remainder of the system is at atmospheric pressure. Now, when the fast valve opens, that simulates the choke valve breaking, we have the high pressure in the air vessel connected to the low pressure of the remainder of the system. So there's a shockwave entering the system and moving towards the liquid slug. Now, you actually see here the opening of the valve. This is the pressure from a simulation model just upstream of the slug. So you have a high shockwave, some oscillations, and after that the slug starts moving. Now, when the slug starts moving through the test section, we actually trigger each of those void fraction sensors one at a time, because they're all located just one after each other. And from that, of course, you can determine the slug velocity, the slug position, and also a bit of the slug shape. So, I actually have a video at full speed of what is happening, because we have quite a high pressure difference here. So there's 1.2 bar upstream and atmospheric pressure downstream of the slug. We don't have sound here, otherwise you could actually hear it coming. So that's actually the slug. It's moving at 22 meters per second, so that's about 9 kilometers an hour. This was actually one of the low pressure experiments. We went up to 4 bar G, where the slug velocity goes up to 35 to 40 meters per second. Now, of course, our first goal was to see how well these experiments compare to our simulations using the Wanda code. First of all, we tried to match our simulations to the experiments when we didn't have any slug in the system, so with gas only. So you only have a shockwave moving throughout the pipeline, some reflections on the downstream tank, and then developing gas flow. And actually the match is quite good. As you see here on the left side, we can actually quite well predict the first upsurge. Magnitude is not spot on, but we actually see the small reflection and some oscillations, and then the developing gas flow. Here on the right, it looks like a really bad match, but actually this difference is 0.05 bars, so it's actually not that bad. Now, if we introduce a slug into the system, things get a bit more complicated. This is a recording of the mass flow rate. Red line is from the model, blue line is from the measurements. And here you see that the development of the mass flow rate is completely different. That the first upsurge is nicely predicted as far as the timing goes, but the model decreases much sooner, and also the eventual mass flow rate is a bit lower. And in the pressure we see the same phenomena, that we actually have a lower pressure in the system than we see in the measurement. And we did calibrate the model, but we actually calibrated on the initial velocity of the slug, because that was our main interest in this experiment. So here we have the velocity of the liquid slug, and this is what we calibrated on to have the shape of the slug match, the shape of the acceleration. And then we actually see something else, in that the position of the slug is actually behind what the model predicts. So our liquid slug is moving slower than we predicted. And that was actually strange, because I was expecting it the other way around. I was expecting our model to give more friction. Now, by then, the main focus of the project actually shifted from being a pure validation experiment, and it moved more and more into how can we explain this difference and what can we do to actually figure out what is causing it. Because the alpha loop is a completely steel pipeline, so you cannot look inside. So the measurements that we did, the pressure measurements and the void fraction measurements, is what you have. So first thing we did is to look up literature and do CFD simulations and look at how we compared to the other ones. This is an image that I copied from a colleague of mine, and what you actually see here, the pink line here, that is my experiment. Red line and green line are two numerical models coming from literature, and the blue line is a CFD simulation that we did using star CCM. I'm not a CFD expert, so do not ask me about details of the CFD simulations, but we actually see that the CFD simulation predicts a higher velocity than the literature model, because in the CFD simulation the slug is actually shedding a lot of water, so it's accelerating faster and faster. And that the experiments, as we also see in the Wanda simulations, accelerate slower than the literature models. Now, so basically we were none the wiser. We still had the issue that our experiments didn't match the model predictions, and the model predictions didn't match the CFD simulations. So, next option, we installed a transparent section in the alpha loop. Same diameter as the steel piping, 6 meters in length, and we used a high-speed video camera to look at the shape of the slug, the tail of the slug, and also for air entrainment. Now, looking at a slug at 22 meters, zooming by at 22 meters per second is not easy. We use a frame rate of 1500 frames per second, shutter speed of 1/11,000th of a second, and the camera that we had could produce actually 4 seconds of video for that. That's more than enough, because within 1 second the entire slug has passed, as you saw in the last video. But it gives you an idea on the time scales of the experiment. So this is a high-speed video recording. This is actually played at 100 times slow motion, at 15 frames per second, where you can see the slug passing by. First thing to notice is that there's actually quite a low slope of the nose of the slug, and there's a lot of air entrainment in the slug itself. It takes up a lot of air along with it. And if you look closely, and now the slug has passed, and this is actually the tail of the slug, but there's a lot of water trailing behind. And there's a lot of water also around the edges of the pipe. And you can see how long there's still water coming by. It's still part of the slug. Right now you can actually see the water slowing down. And in the center it's still flowing at high velocity due to the air. Okay. So, like I mentioned, we noticed three things. There was a very turbulent nose of the slug, really sloshing about. We had severe air entrainment in the slug itself, and we had a very turbulent tail of the slug, dissipating a lot of energy. Now, of course, knowing what causes the lower acceleration doesn't explain why we have it, and why our validation data doesn't match the experiment as well as data found in literature. So, it can be caused by a few things. By geometry of the pipeline, as you see here. The slug was created by having a local depression in the system. That means that during the first moments of acceleration, the slug has to pass through bends, two bends. Problem could be the void fraction sensors, which actually have, of course, the two metal wires inside the flow. So they can cause the air entrainment, they can cause the sloshing of the slug. And of course, as you see also in the 3D model, to have all the sensors in the system, there were a lot of flanges. Of course, they were aligned as well as can be, but you still have maybe a millimeter or half a millimeter of an edge at each flange, which of course can cause some turbulence. Now, so, a lot of work we still have to do on this. We have done the first analysis of the data, but we have over 140 measurements, and for 3 different variations for a variety of upstream pressures and slug velocities. So there's a lot of work to be done. We still cannot explain some of the high resistance that we saw in the test setup. That's still an issue. And the energy losses in the slug were higher than expected. We have some explanations for that, but we would like to see more and be able to reproduce it in our model. We also found we need to improve temperature measurements to try to measure gas temperatures, dynamic gas temperatures in the system. And we mainly saw that where the model predicts a very high oscillation of the gas temperature, in the measurements you don't see any variation of the gas temperature. And also, we would like to improve some of the mass flow rate or the velocity measurements, because at the moment the mass flow rate sensors that we had weren't producing accurate results, and predicting the mass flow rate based on the pressure and temperature in the upstream tank. We can actually predict, of course, the mass flow rate flowing from the tank by looking at the pressure decrease. Is not an accurate way to record mass flow rate. But the physical behavior that we were simulating here was actually quite well simulated by the model. We were seeing all the reflections that we were expecting to see. The model predicted the slug velocity actually quite well. It was within margin of error of the experiments actually. And overall, we were quite satisfied with this first validation of a completely new module. Now, of course, there are some things we would still like to do and what we're looking for in the future. We are currently working on automated calibration of Wanda models based on measurements, and I think that would significantly improve the matching of these validation experiments. We are currently looking for other more literature data on large-scale experiments. Most of the literature data that's available for these type of experiments is based on 10mm piping or maybe 50mm piping, so small scale, and not the 200mm or higher that we are looking for. And we were looking to repeat these experiments, or maybe a variation thereof, with additional sensors in the system, such as mass flow rate sensors, and maybe an optical way for measuring temperature. That's something we're looking at. That was my presentation. If you have any questions, please.